Okay, good morning. Tuesday morning, 8 o'clock. Welcome to this session toward a resilient global society. My name is Ben van der Pluim. I am hosting this with Amir Akaguchak. We have a lineup of 6 very interesting talks coming up on very different aspects, but all sort of brought together with this idea about resilience. And at this meeting, of course, as you are undoubtedly aware, there'll be enormous numbers of talks about looking forward and how we should live. In fact, at this room yesterday, there was a big session on how the future might play out. But perhaps it's also nice sometimes to look at how today is playing out. The sort of difference between sustainability and resilience in many ways is about looking forward, and resilience is more looking at it today. And there's a lot of lessons you can learn. I just have a sort of definition on this in case you wondered what resilience was as opposed to other topics. But really the bottom line is to just live with the changes that are around us, to basically be able to absorb them and to actually learn from these experiences. And that's what the focus is of this session, of trying to be at least looking at the shorter term changes that are taking place around us. And what we've done is we've collected a rather eclectic set of speakers, I should say topics. I don't know whether the speakers are eclectic, but eclectic set of topics, but they're really major, huge topics, and they are sort of a lot of people's minds. They are forefront of our thinking in the sense of the issues that we have to deal with right now. And so what we'll do at this session is, as you can see at the bottom, there is a I'll put that little slide up. As you see at the bottom, there is a way if you have questions in this session, and hopefully the speakers will every now and then remind you as well. You can email your question. We do not have a stand-up question series there. There's just not enough time in some ways, but we have a panel at the end of this series of talks where we'll have a conversation with these with the 6 speakers. And so if you have a question, email them to that particular address, resilience.earth@gmail.com, and they'll come to us, and then we'll with Amir and I will organize this in the conversation part of this session. As you can see, you can also go ahead and use your Twitter account to express your opinions, the names, and I'm not sure they want that, but now it's up. You can actually get a hold of them that way. That's how we organize that as well. Okay, so it's 1 minute to go. We'll settle this up. Speakers, you have 14 minutes for your talk. There's 1 minute to switch over. And then, as I said, the question period will be afterward. And hopefully we don't get confused. I don't get confused too much with all these buttons to press, but bear with us. Okay, Andrea Dutton is our first speaker. Andrea. Set this up. See, that's it.
It's peasy.
Excellent.
Can I use that or not? Okay, yeah. Okay, good morning. I'm really excited to be kicking off this set of talks in this session this morning. So a lot of the topics that you're going to be hearing about today, not all of them, but several of them, have been exacerbated by this incredibly pernicious yet very slow-moving threat that some people have referred to as the defining issue of our time, and that is the threat of climate change. Right? But unfortunately, the problem with this is that humans are not very well evolutionarily adapted to dealing with slow-moving threats, right? We're adapted to respond to urgent threats that are in our face, like a predator that's stalking us in the woods that locks eyes with us thinking about its next meal, right? I mean, you don't get that visceral response when I say the words climate change, right? And it's such an abstract topic, you can't really see the temperature change in the way that you can see this predatory cat stalking through the woods. But just the same, it's moving slowly like the cat is until that cat pounces, right? And climate change is on your doorstep in the form of a wildfire or a heat wave or flooding, which is what I'm here to talk to you about today, is about the challenge of sea level rise and to think about this interface between the scientific knowledge that we have about sea level rise and how it interfaces with building a more resilient society. So when we think about sea level rise, it is actually one of the more visual ways to think about climate change because you can see all these pictures of places getting inundated. But one of the problems with that is people think that the only threat from sea level rise is inundation itself, when as you can see from this list, is there's actually a complex array of challenges that it poses to us, and solutions that might meet one of these impacts will not necessarily meet all of them. So for example, if we build a seawall to prevent our coastal property from getting inundated, that won't prevent that water from coming in underneath and intruding our freshwater aquifers. So if we are going to become resilient in the face of this challenge, it means addressing all of these topics at once. Okay, so the biggest question in the field of sea level rise is how much and how fast? And it's a really sticky question to answer, right? But there's one thing that we know for sure, is that when we look at the past century at the rate of sea level rise, which was on average about 1 to 2 millimeters a year over that time frame, is that sea level rise has been accelerating. And even over the last 25 years, where we've been measuring sea level using satellite altimetry, that record is now long enough for us to detect an acceleration signal in that. And the average over that time frame is about 3 millimeters a year, but it's been rising. And that acceleration is mostly driven by the melt coming off of Greenland and Antarctica. All right, so the thesis of my talk today is really twofold. And that is that to achieve resiliency in the short term requires two things. The first is that we account for the longer timescale processes that are affecting sea level rise, but also the shorter term processes that are going to superimpose on top of that. Secondly is something that is altogether different, and that this problem is created essentially by humans, that of climate change and sea level rise. Therefore, the solution is also going to very much lie with humans. And so that we as scientists will not be able to help people build a resilient society until we acknowledge and address the social and psychological aspects of what it's going to take for humans to engage and implement those solutions. Okay, so first let's look at some of the longer timescale processes, and this is kind of the bread and butter of my research. I mostly look into the past, at past warm periods, trying to understand how sensitive these ice sheets are to sustained warming. And so this is a cartoon that we came up with in a review paper from a few years ago, where we explain the sea level budget of a time period known as the last interglacial, about 125,000 years ago. And as you can see, there's some component of thermal expansion. We can melt all the rest of the mountain glaciers that we have on the Earth today. Greenland melted a little bit, maybe 2 meters worth, but there's a lot of uncertainty on that, as you can see from the diagram. And then what we see from the coastal records in the far field from these ice sheets is that sea level rose to somewhere between about 6 to 9 meters is our best guess. And to get there, that would have required a very large contribution from the Antarctic ice sheet. But again, the uncertainties are large, right? And if you add those uncertainties together, we're really uncertain about the degree to which Antarctica contributed to this. But nonetheless, and even if we're off by several meters, there are some important lessons from this example in terms of building a resilient society around this. That is that the warming that we've already seen today, because during the last interglacial, average temperature was about what it already is today. So the warming that we've already done may have already committed us to something like 6 to 9 meters of sea level rise. The good news is that will not happen overnight. But what that means is that the sea level rise that we see today, or even to the year 2100, is really just the first step in what is going to be a very long journey. And so if we have a solution that will solve the problem over the next decade, it needs to be adaptable and scalable for it to be also sustainable into the future. The second is this begs the question of what is the nature of this sea level rise going to really look like, right? Is it going to be gradual, or is it going to be stepwise? Are we going to get a sudden collapse of some sector of the ice sheet? So let's turn to some of the research that's being done in the ice sheet community. And the overall message from this is that the more we learn about these ice sheets, the higher our projections for sea level rise get, which is not good news. All right, so there are three aspects I want to look at here of research that's been done in the recent years. The first is there are a couple of papers several years ago now that looked at this question of, has the collapse of the Western Antarctic ice sheet already begun? These authors thought that it had already begun. Now, the problem with looking at tipping points like this is it's really hard to identify a tipping point until you're past it. And you can say, oh, there it was, right? And we're on the other side of it now, right? So you can debate this. Are we at it? Are we just past it? We're probably very close to it, and regardless, right? The next part of the story is that how fast this plays out will very much depend on the importance or the sensitivity of two physical processes known as hydrofracturing, which is due to the surface melt that we're now seeing in Antarctica and Greenland, or ice cliff failure, how important those processes are. Because if those come into play, the models are showing us that the rate of retreat is much faster. So instead of millimeters per year of sea level rise, we would be looking at centimeters per year. Okay, thirdly, there's a paper that actually came out last week in Nature that looked at the Greenland ice sheet. And these authors, which we know is a growing contributor to sea level rise, as I mentioned before, said that a recent ice mass loss is dominated by surface meltwater runoff, that process we were just talking about, and that showed a nonlinear response to the fairly linear trend in temperature that you can see on that diagram up there. But the two melting profiles underneath, in the orange and the red, show a sudden increase in melt after about the year of 1975. And we also know from the paleo record that ice sheets can behave non-linearly. You can get large jumps in sea level like we saw during the last deglaciation. And now we're seeing some potential for nonlinear behavior just in the very recent past, right? And that's a very challenging thing to become resilient to if we don't know how large those steps are going to be. So now let's think a little bit about these shorter timescale processes. I'm going to walk you through a quick case study on the US Atlantic coast. And on the far left side of the screen, you can see an image that came from a publication by Asbury Salinger and colleagues several years ago, where they identified what they referred to as a hotspot of sea level rise north of Cape Hatteras. And this is an area where sea level rise was accelerating faster than in other areas along the coastline. They attributed this to a change in the speed of the ocean currents, the Atlantic meridional overturning that the Gulf Stream feeds into. And this is the physical expected response. As the Gulf Stream slows down, more water should pile up exactly along that portion of the coastline. Right? So I was involved in another paper that came out last year that you can see the figure on the right, where we looked at these hotspots. And when we looked at the tide gauge record, we could see evidence that as you go back in time, you can see that these hotspots also occurred sometimes in the south and not just in the north, even though they mostly were up here in the period of time that they looked at in the previous paper. Now, this time series ends at 2010. From 2011 to 2015, this pattern of it being focused in the north flipped to the south. And in fact, these are some tide gauge data between Miami and Cape Hatteras. These ones are mostly in Florida, where the rate of sea level rise increased by almost an order of magnitude. And we saw 5 inches of sea level rise in only 5 years, right? So for context, 3 millimeters per year is about 12 inches over a century. And we got 5 inches in 5 years. So it's at this point in the conversation when I'm talking to a coastal planner that they stop blinking and their eyes start to pop out of their heads, right? They are not planning for 5 inches in 5 years. Yet we need to realize that this natural variability exists in the system, and you can get these rapid accelerations and decelerations around the longer term rise in sea level that's driven by climate change. All right, so that's the important takeaway message in terms of preparing and becoming resilient to it. All right, so this is really the main planning tool that scientists usually take when they go to talk to coastal planners, and they put up some sea level projections and they give an array of curves. Now, there are two real challenges I see in using this tool and communicating with these people what it actually means. And the first is an issue of baselines, right? So this is relative to a baseline where it intersects the 0 and somewhere around the year 2000. So there's a community in South Florida that I've worked with before that's planning for 2 feet of sea level rise by the year 2060, right? Well, that's 2 feet above what it was when it crossed that 0 line. So if communities were already getting flooded, as many of them are, 1 or 2 feet of sea level during the king tide season when the tides are higher, that means 2 feet on top of 2 feet. Now you're at 4 feet, right? And that would cover the head of my child, right? Which is a totally different matter than thinking about only need to worry about 2 feet of sea level rise. So this issue of baselines is an important one to remember. The second thing is that I can guarantee you that sea level rise will not look like any single one of these curves, which is a little bit surprising for me to hear, because sea level does not behave like a smooth curve. It looks like this, right? This is a tide gauge record from Virginia Key, which is in Miami. And you can see here there's an annual signal where you go up and down. You get the king tides in the fall and is lower in the spring. And you can see some large peaks in this diagram. These are the hurricanes that have passed by, right? You can see Hurricane Irene, Hurricane Wilma. So these are the storm surges that you get on top of the base level of sea level rise. Then we get that rapid acceleration from 2011 to 2015, and boom, we get just a normal high tide at the same level as a hurricane storm surge. right? So when we think about how sea level is going to rise, what it means is we are going to hit, say, 2 feet with an increasing frequency until we are on average at 2 feet. It doesn't mean we won't hit 2 feet until we get to that point in the curve. And that's a messaging issue, which is why I think thinking about it in terms of frequency of coastal flooding, how many days of a year are we flooding, is a more useful framework in terms of thinking about how we become resilient to that and what we can tolerate, right? Okay, so the answer to how much and how fast is I usually tell people it will happen faster than you think it will, because we will hit that level before the year 2060. It's just that we will hit it with an increasing frequency. Right, so here's kind of a compilation of all these points that have come up through the talk about that we need to consider to build a resilient society in the face of the challenge of sea level rise. But the missing ingredient, I would argue to you, is how do we motivate people to take action at a level that will keep pace with, or hopefully even stay ahead of sea level rise? Because there are a lot of different ways to address this. And I'm not going to talk a lot about solutions today, but there's a dizzying array of them in this infographic that you can see on the right. And most of the communities that are really dealing with this problem head on are ones that have suffered from a recent crisis, right? Because again, as humans, we respond to these immediate, urgent threats. Instead of being proactive, we are reactive. Right? And we need to somewhere make this transition to becoming more proactive about this slow-moving threat. Now I'm going to say something that's going to get me really unpopular. I was actually hoping I would run out of time and I could skip over this. But what I've seen in communities is that when they start getting flooded, it starts becoming a really big problem for people. Their knee-jerk response is, let's build a seawall, right? They go into this build me a seawall frenzy. And as a general rule, hard infrastructure like this promotes more coastal erosion that actually makes you more susceptible to flooding. And it also builds in this sense of complacency if you're living behind this wall, because you think I don't need to worry about it. But one day, the time will come when that wall gets breached, right? Think New Orleans in Hurricane Katrina, right? Do you want to live in a bowl, right? So that ensures that when disaster strikes, it will be actually more catastrophic. And this is not a recipe for resiliency in my mind. So finally, I'm going to leave you with these 2 images of postcards from a 1-degree world, which is what we are living in now. And our challenge as scientists is to explain science in the way that we can respond to the urgent threats that you see in these images, so that we don't have to wait until that cat pounces for us to respond. Thank you.
Thanks, Andrea. We do not have questions for those who are late entering. You can send your questions to resilience.earth@gmail.com, and then we'll have a panel session afterwards. And so our next speaker is going to be Susan Annenberg.
Okay, good morning, everyone. My name is Susan Annenberg. I'm from George Washington University. Thank you. And I'll be talking about estimating the health impacts of air pollution to inform decision-making. And just once again, wanted to put up the email address here for questions. So as many people know, air pollution is currently considered the leading environmental health risk factor globally. Over 90% of the world's population is living with air pollution levels that are above the World Health Organization guideline of 10 micrograms per meter cubed. Ozone and PM 2.5 are the key air pollutants that are currently considered in the global burden of disease analysis, and both of these pollutants are high around the world. This is not a problem that is limited to any particular socioeconomic status. Air pollution is a top 10 risk factor for most countries around the world, including the United States. And you can just see here the bar chart from a recent global burden of disease analysis showing where air pollution levels fall regarding some of the, in the context of some of the other risk factors that affect global public health. And the reason we're able to estimate the burden of disease globally from air pollution is that we've had recent advances in ground monitoring, in modeling, and in satellite remote sensing that enable us to understand fairly well at this point what exposure levels are for everyone around the world. So we now have these nice estimates of the global burden of disease from air pollution. And yet, these estimates of the air pollution disease burden are likely underestimated. And that's because in the current global burden of disease, there are only 6 diseases that are currently estimated for air pollution: stroke, ischemic heart disease, chronic obstructive pulmonary disease, lung cancer, lower respiratory infections, and diabetes. And you can see the share of the incidence of these diseases is quite large for air pollution, up to 37% for COPD and 42% for lower respiratory infections. And yet there's an array of health outcomes that we know from epidemiological analysis and other types of health studies that these health outcomes are linked with air pollution. They just haven't yet been included in the global burden of disease assessment. So we have estimated now the global burden of air pollution on new cases of asthma among children worldwide, finding that about 13% of new pediatric asthma cases are attributable to nitrogen dioxide pollution around the world. There have also been recent estimates of the impact of air pollution on low incidence of low birth weight, and there's an array of other diseases that we don't have estimates yet for linking the air pollution to the burden of those diseases. So this is, air pollution is a problem that is currently considered the leading environmental health risk factor, and yet it's dramatically underestimated. The other thing I just wanted to point out is that if you take a look at the bar chart that I showed in the first slide, you won't see climate change on that bar chart. Part of the reason for this is that we still don't have methods to estimate many of the health outcomes that are expected from climate change. Another reason is that climate change is effectively a threat multiplier. It acts through other risk factors that are included in the global burden of disease assessment, one of which is air pollution. So climate change and air pollution interact in several ways, and I just wanted to talk through some of those interactions. First of all, climate change can impact air quality through changing meteorology, photolysis rates, and also emissions, both anthropogenic, things like increases in air conditioning use, as well as what's currently considered natural emissions, but we have growing recognition that some portion of these natural emissions is also anthropogenic. Things like wildfire PM, dust concentrations, and biogenic volatile organic compounds. Air pollutants also influence the climate by absorbing radiation, interacting with clouds, changing the planetary albedo or reflectivity. And then, of course, many air pollutants and greenhouse gases share common emission sources. So if we were to go after just greenhouse gases, some of the mitigation measures we might undertake would also reduce air pollutants. So the good news here is that there's a lot of opportunities to achieve co-benefits for air quality, for climate change, and for public health. So I'm going to talk a little bit about how climate change will impact air quality in some specific ways, and then talk about some co-benefits. One of the challenges I think we've had so far is that we have sort of understood that climate change will impact air quality in a number of different ways, but we haven't had methods to quantify the degree to which climate change will exacerbate these problems or to quantify the health impacts that would occur. We have known for a while that climate change will exacerbate ozone, perhaps cause longer pollen seasons, increases in smoke from wildfires, and increased dust concentrations. But how bad will those effects really be, and what will be the impacts on public health? So that's what we've been attempting to quantify. These are some of the results that my postdoc, Polyaja Kolwasset, showed yesterday, increasing dust concentrations and associated health impacts in the Southwest US in a changing climate. And you can see here on the left, this is under the climate scenario RCP 4.5, sort of a middle-of-the-road scenario. We used historical statistical relationships between soil drought index and dust concentrations over the Southwest US, and then output from 6 climate models through 2100 under 2 climate scenarios, RCP 4.5 and 8.5, just showing 4.5 here, to project how these increases in drought conditions and soil drought conditions will influence dust concentrations in the future. And you can see here that we do expect increases in dust concentrations. All 6 models predict the same thing, basically. There's a bit of a spread in terms of the degree. And then if you take that a step further and estimate the health impacts resulting from the additional PM 2.5 exposure, and then convert that into dollar values, we estimate about $34 billion in additional economic damages under RCP 8.5 from climate-induced changes in dust concentrations just over the 4 states included in this analysis in the Southwest US. Now, the magnitude of this was a bit surprising to us. This ended up being the fourth largest impact of climate change in the United States, behind extreme heat, labor, and coastal property, at least considering the sectors that are currently included in the US EPA's Climate Change Impacts and Risk Analysis report. So this was quite substantial if you consider the fact that this is only 4 states in the Southwest US. So I think this is an important climate penalty that hasn't been widely recognized yet. Another one is the influence of climate change on wildfire PM. So this is a paper that came out in GeoHealth a couple months ago, showing fire PM 2.5 in 2050 and 2100 under 2 RCP scenarios, RCP 4.5 and 8.5 again, compared to the year 2000. And you can see that wildfire PM 2.5 increases quite a bit in the southeast US, as well as the western US and the upper Midwest. And again, if you take this a step further and estimate health impacts, you start to see some really interesting features here. If you take a look at the bar chart on the right, this is the total PM 2.5 mortality per year in the United States. And you can see that it's declining over time. And again, this is a result of our effective regulations on air quality, assuming they continue, that we are controlling our anthropogenic emissions, which brings down total PM 2.5 mortality. But if you take a look at the bars in the future, a larger portion of those bars is contributed by wildfire PM, both local to the United States as well as transported fire PM from other countries. And if you just take a look at the rightmost bar for RCP 8.5 and 2100, wildfire PM becomes the dominant contributor to the total PM 2.5 burden in the future. So I think this is another climate penalty in addition to dust that will make it harder for the United States to attain the national ambient air quality standards and protect public health in the future. So what can we do about this? Cities have been looked to now as sort of a new frontier in climate mitigation. And also the co-benefits literature really highlight the opportunity for cities to attain co-benefits for local air quality and for public health. And yet there haven't been estimates made in a globally consistent way of the total PM 2.5 burden in cities worldwide. So that's what we set out to do here, and we found that only 19 of 250 major cities have PM 2.5 concentrations that fall below the WHO guideline. And we also found, if you just take a look at the bars on the bottom, you see a 10-fold variation in the rate of PM 2.5 mortality among these 250 cities. So this indicates that some cities are doing better than others in terms of their PM 2.5 mortality rates. And so it can be done. The question is, how do we do it in a way that we're also controlling greenhouse gas emissions? So we took a look at the PM 2.5 death rate in these 250 cities compared to CO2 emissions. And we found a significant positive relationship that you can see here, but there's quite a bit of scatter. So if you take a look at the dots above the line and below the line, there's a bit of clumpiness according to regions as well. So we wondered, well, what's going on here? So we took a look at comparing PM 2.5 concentrations and the PM 2.5 death rate against GDP per capita at the city level. And we found that as cities get richer, PM 2.5 levels go down. So, as cities get richer, they tend to clean up their air pollution. But if you take a look at the third panel, this is CO2 emissions against GDP per capita, there is no relationship there. So it appears to be that cities are, as they get richer, they're cleaning up their air pollution, but not doing much for CO2 emissions. So I think there's a couple explanations for this. One can be seen in the fourth panel at the bottom here, which shows carbon footprint. So carbon footprint accounts for goods that are consumed locally but produced elsewhere. And we do have a positive relationship between GDP per capita and carbon footprint. So this indicates that rich cities are essentially exporting their pollution to other cities that are manufacturing the goods that they're consuming. But I think there's another lesson here, and this goes back to the definition of resilience, that we need to learn from the past to bounce back stronger in the future. In the past, we've implemented mainly end-of-pipe emission controls, things like diesel particulate filters, scrubbers. These are sort of the simplest and cheapest things to do to take air pollutants out of emissions. But of course, they're not doing much for CO2 emissions. So what we really need to do in the future is really burn less fuel. And there's the good news here is that there's many ways to burn less fuel. We can displace motor vehicles with active transportation, move to zero emission energy, increase our energy efficiency. This is actually the building I work in, the GW School of Public Health, that's very energy efficient. Oops. And then the last point I'll make is that the health benefits of mitigation are often unknown. And yet the large burden of disease from PM 2.5 results from the fact that there's a very strong relationship between PM 2.5 concentrations and mortality. So if we were to be able to estimate the health impacts of changes in PM 2.5, whenever we're making a decision that will influence PM 2.5, the benefits would be quite large compared to the costs. So this is the benefits and costs of US clean air regulations, and you can see how much the benefits truly outweigh the cost here. And yet tools to assess those health benefits of air quality improvements are not widely available, especially to decision makers at different levels, like at the city level or at the national scale in many countries around the world. We're also excluding health from our estimates of the societal damages of climate change. And again, if we were to include these pathways by which climate change will influence air quality and then health, the social cost of greenhouse gases would increase substantially. And then, of course, we have fragmented decision-making. So we have ministries of transportation and energy that are making decisions that affect air quality without knowledge, without quantitative estimates of the health impacts of those decisions. So I think these are ways that society can become more resilient to the impacts of climate change on air quality that we're anticipating. So just to conclude with some key messages, that air pollution is among the top risk factors affecting public health globally. There are some future climate penalties for both PM 2.5 and ozone that may make it harder to attain national ambient air quality standards and protect public health. The good news, though, is we have many opportunities to achieve co-benefits, particularly in cities where we have large populations that are exposed to high pollution levels. But we need tools to be able to quantify those health impacts so decision makers have the full information they need to make effective decisions. Thank you.
Thank you, Susan. Just as a reminder, with questions you can email them to resilience.earth@gmail.com. We're just going to have the speakers follow in a row. The next topic is going to be on water, and it's Kaveh Madani. Where he is. There you go. Big step. Oh.
So I think I need to start with removing plastic bottle water away because I have a track record of banning that in Iran, so I don't want media attention to that. But it's funny that we made this one plastic free, but we're still having plastic in the rooms. To give you a background on my talk might sound like a social science talk, but I'm not a social scientist. I'm an engineer by training, and over the years have got more and more into the human side of things. And not long ago, I served for a short period of time in politics as one of the very high levels, unusual for academics. I was the deputy vice president of Iran and the deputy head of Iran's Department of Environment. Got accused of being a spy because I was talking too much, I guess. And then I had to run away and was in hiding and recently came out of hiding. Still don't know where it's safe for me. So I'm going to share some of the things and findings and observations I had in the policy world. And as a scientist being there and really being a spy on government and seeing what's going on, I think those are worthy of sharing. So I hope I don't disappoint the host who invited me to this session to talk about water. I talk about water, but very briefly. I'd like to talk about resilience and other matters. As a reminder, you can send your questions to this email address before 9:30, I've been told. Talking about water, I mean, we heard two talks, one about sea level rise, one about air pollution, now about water. When it comes to water, to me, the world is also ending. The sky is falling. The situation is really bad. We don't know that whether we have passed the tipping point or not. The situation is horrible. And in my world, I think without water, none of the other, it doesn't matter what else you have done for the society, you cannot run forward. So I call it the water bankruptcy problem. I even think it's not a crisis anymore. We are past the tipping point. We cannot recover from, in many cases, and we cannot restore the system in many cases. So beside mitigation, we also need adaptation. We have learned it in the climate change world, but not in the water world, as we are still trying to find more and more resources and damage more resources. Now, as I said, in my world, without water, you can't function, and doesn't matter. I mean, I think the difference between me and the first speaker is like she sees too much water, I don't see any water. Speaking about these things, I want to get your attention to the fact that society is full of problems and resilience is not about one sector. But in my world, so then I have all these fancy suggestions as other water people and other people in water management. Some of us do different things, but if you're an engineer, you always want to go for more technology, new resources than as economists or policy people. You talk about removing subsidies, you raising prices, change all the existing things and the existing settings of institutions and do things differently. And through this, you can save water. You can restore some of the existing systems, help with the aquifer recharge, et cetera, et cetera, et cetera. And people are really, I think, tired of these things because they hear them on and on, every day, on a daily basis, and everyone is good in theory. But that's my world. And in my world, then I go and try to find what's fair, how this should be done in an equal manner, in a fair manner, implement justice, and we always come up with, more and more solutions. We try to think about all these stakeholders, all people who are using water in some sort. We know that these problems are multi-objective problems or many objective problems. We take into account those and then go for the group consider the group rationality and try to maximize the benefits for all, and then as a person who prescribes for the society, I come out with good solutions in the water sector and want the policymaker and people to listen to me and do it. Now, when I do it as a scientist, thinking into the, with foresight into the future, I think about cooperation, maximizing total benefits of the system, and also long-term benefits. Now let's go into the policy world, where cheap talk is an option. You can make good promises and gestures and all these things. And if you look at what the politicians say, in many cases they're making promises that we as scientists even think they're too ambitious, even in the environmental world, whatever they talk about. A good example, 2015, Paris Agreement and all these things. And just so you know, I was one of them at some point. So I was in the last round of negotiations, head of the Iranian delegation, where I was actually in those negotiations trying to get some attention also to the water matter, because as a water person, I think Paris Agreement totally ignores water as a component, and because it's energy dominated because of the politics there. But there, you make a lot of good promises, and talk about things. But now, what do you deliver those? Right? For them, for the politicians, a lot of times we think they're stupid, we think they're irrational, we think they don't know what they're doing, but their word is different. Their word is not about cooperation necessarily, full cooperation among all parties, because you take advantage of competition, you take advantage of conflicts, and that's healthy to your survival, to attention to you, and so on. And it's not about long-term benefits, it's about short-term benefit maximization. That's a different world. Whether we like it or not, that's how things function. Now, in their world, so when I say they understand that water shortage exists, they understand that water is a problem, but my solutions to them are not helpful. Why? Because when I talk about water, I only see water, but in their policy agenda, Oil and energy makes more sense because it's about short-term benefits. It's about economy. It's about visible effects on the economy. Food matters to them, but you cannot only talk about water. In some parts of the world, food security is even a political issue in a place like Iran, for example. How about the economics of the agricultural sector? See the trade war between the U.S., China, and all these effects on the global economy, and then you tweak something in one sector. So the economy and matters. I mean, U.S. indeed actually manipulates the whole world crop price and commodity price in many cases. So there is a war there. And when I talk about water, I ignore them. But the policymaker sees all these things, actually. So then how about jobs? Am I considering the number of jobs which are tied to the water sector? And any reform in the water sector, in the agricultural sector, means a loss of jobs for people. Do I see the facts about inflation, how this affects my economy when I talk about removing subsidies, raising prices, and so on? And then now the question is, right now at this point in time, which one of these guys is more popular? We make fun of Trump, we make fun of his policies and so on, but he is communicating to the public who care about the things that he cares about, and they have a good relationship. Whereas Macron seems an unrealistic guy, too ambitious, making a lot of promises about cutting carbon, doing this, doing that, and raising taxes, thinking about long term, and so on. What's the difference? And now in this situation, now the guy has to back up, change his policies, whereas Trump is getting more and more aggressive in many cases because of the support he has from the public that we are ignoring in many of our situations. So I want to argue that many of us live in our superficial life and boundaries, and we set boundaries for our systems while we're dealing with a super complex system. So the boundaries I impose on my problem don't exist. Water is not really water, and if it's water, it's just part of a big system. Perfect cooperation does not exist. People do not make decisions based on group rationality. And these are the facts that we are ignoring. So we are dealing with a super complex problem. I only deal with water out of this system of systems of human nature system of systems, which is a super complex thing. Now, within this, you have smaller dots, which is air pollution, sea level rise, climate change, water, and all these things, right? So food is one sector, energy is one sector, but you also have other sectors, like, toward the left, jobs, economy, politics, inflation, like other matters, like how you dominate in other parts of the world, war, like all these things that we ignore. Now my word is water, or if I claim to be very interdisciplinary, I'm somewhere at the nexus of water, food, energy, environment, and all that. But the politicians are hanging out somewhere else that is more important, because they're thinking about re-election. They're thinking about the things which matter to the society in the short run. But how do you determine what matters to the society, and how do we deal with that? So in this environment then, my solution to them is garbage. They even think I'm manipulating them. I'm a spy working for Mossad and CIA, trying to make, to ruin Iran and give bad solutions. And the same thing, right? We think that some of the solutions given by the policymakers are garbage and don't function. So then we get into this battle of who's smarter, who's not, who's more emotional. But the reality is that we can stand on both ways. We can be the people who don't understand the public. We don't understand what's happening. Look at the whole world and the things we missed about Brexit, we missed about Trump coming out of the election, all the extremism that we're seeing in different parts of the world, in places that we thought people understand the value of society, value of cooperation, value of democracy, and so on, right? And all of these, my argument now is it's a counterintuitive finding for me as a person who always was very proud, I would say, or I thought I was successful by hanging out at the science policy interface. At a science policy interface, you get you even put it in your tenure package, and you're proud of the fact that you're asked to testify in a parliament or talk to a parliament member or go to this minister. Your research results are being observed by them. They pay attention to it, and it feels good. Media picks it up, and so so on. But the reality was that when I was sitting at that position, I had the authority to make decisions. I knew a lot of problems. Of course, there are the issues of priorities, right? Do I deal with air pollution, which is a visible problem? People are suffering right now, or water, which is a long-term problem. It's not visible most of the time. Do I deal with climate change in a country like Iran at the moment, or many other problems I have in pollution, waste, like biodiversity losses, and then jobs, economy, sanctions, and all these things that I'm dealing with. And then it's the issue of priorities. And who determines the priority? So we have the chicken and egg problem. In order to have people who care about climate change and environment and water and all these matters, we have to have governments who care about education, informing people, bringing these issues up, telling them about the future and what matters, and how it affects their lives. And in order to have politicians who are that way and climate sensitive or environmental sensitive, you have to have a community of people who care about those matters, right? And this is where I see our role. And the question for me is, do I really hang out with the people I need to hang out with? Do I really communicate directly with the public rather than being proud of, going to the minister's room and briefing him on my results or her on my results? Do I talk to the people who are affected by our decisions? Because once they know, and this was my trick when I got into this job, that whenever I wanted to move my agenda forward, I was talking to people directly. I was trying to create a sense of urgency. I was trying to create a sense of partnership, giving them a role about the things that matter, their opinion on things, their solutions, and so on. So the reality is that we need to put pressure on and weight on the shoulders of the policymakers. But to do that, we need to keep the sensitivity level of the society high, and it's really hard where you're dealing with a range of problems. Disasters are good. Extreme cases are good because that's like, for a limited period of time, the weights are on the shoulders. But they go away quite quickly if you don't continue insisting and working on them. And I want to conclude my conversation with this, that let's not misuse the term resilience as we did in the case of sustainable development. These terms are not too different, honestly. It's just like these are cycles. We go from one term to another. Resilience, like sustainable development, is a system of systems concept. It's about the whole system. It's not about pieces. And we often make a mistake that we think the summation of sustainable pieces is sustainable, the summation of resilient pieces is resilient, and that's not true. Thank you.
Okay, thank you. As I said, you can send your questions to that address over there. Our next speaker is Christine Goulet. She's talking about earthquakes. Will you go this way?
Yes. Reset the... Okay, thank you. And the slides not showing. Good morning, everyone. Thank you for coming in this early morning session. Thank you, Ben, for inviting me. Today I'll talk about how earthquakes can affect society and how we can learn and apply scientific research to really improve resilience. What I'm going to talk about today is really the work of a lot of people. So I'm just presenting results from a large community of people all working together to help resilience. So I want to first introduce you to the Southern California Earthquake Center. We're based at the University of Southern California, and our mission is really to solve problems in earthquake system science. So we talked a lot about systems today, and it's true. We use Southern California as a natural laboratory. Of course, we have San Andreas Fault there, the whole system, and multiple faults that you probably have never heard of that might be more of an issue for us. And we use that to gather information from all types of sensors and data collection, studies, and lab experiments as well. We synthesize our knowledge into models that better represent the physics of what's happening during earthquakes, and I'm talking about micro scale and macro scale as well. And then we communicate that understanding of the earthquake system science to society and to stakeholders so that we can have an impact on resilience. So we're a large collaborative center. Collaboration and multidisciplinary is what defines SCEC. And today I'll give you examples of how we can really work together to have an impact on risk and resilience. So it's really important that we have all those disciplines from geophysics, earth sciences, computer science, engineering, all that, everybody working together to try to better understand the world and have an impact. So we support at our center both fundamental research, applied research, as well as very strong communication, education, and outreach activities. So over 1,000 participants, lots of institutions around the world and in the US, and so on. So everybody has a different definition for resilience. Not inconsistent with what Ben has presented, but I want to present this here from an engineering perspective. So we tend to quantify risk in terms of 3Ds, so to any event. So the 3 deaths, so deaths, dollars, and downtimes, with rate of exceedance and so on, and probabilities associated with them. So this is done in a probabilistic framework. We can talk about the hazard, and really here, that's what we do at SCEC. And I'll talk mostly about ground motion hazard, although there's a lot of other hazards that get triggered as well. You multiply this hazard by the exposure. Is there human infrastructure that is in the area where you expect the hazard? And then you multiply by the vulnerability of that human infrastructure. Is the building, the freeways, are they fragile or resistant to large ground motions? Then you divide that by resilience, which is the ability to society to bounce back after an event. So earthquake system science really works on characterizing the seismic hazard, and by that it affects risk by reducing it, by reducing uncertainties, by a better modeling of what's happening, and increasing resilience. And also using education and preparedness to increase resilience. So those are the ways we can impact society. So one of the things we're pretty good at SCEC, I'd say we're very good at, is in this combination of information to models, we do a lot of ground motion simulations. It's really important to validate them so they can be used. But I want to talk a little bit about the main ingredients I use in the ground motion computations, because you'll see some examples of how we have impacted resilience so far. So you can define the problem as first you have earthquake sources, so faults, and their location, geometry, the magnitudes they can produce, their slip rate, and all that is important to characterize. And we use an earthquake rupture forecast. You'll hear more about that in a second. Another way we integrate information is by developing 3D velocity structures or models of the Earth to capture the large-scale heterogeneities, as well as if we have sedimentary basins, how waves can get refracted, reflected, and trapped in there and affect ground motions. And then we can calculate the wave propagation, attenuation, site response, and all those things together to come up with ground motion simulations. Again, validation is extremely important. So I'll talk about a few examples of simulations. The first one I want to talk about is something that we did more than 10 years ago. So why is it still relevant? You'll see that in a couple slides. But the Shakeout Scenario is developed as an exercise. The scenario was defined as a magnitude 7.8 in Southern California. And you can see here the Mexico border, and the map extends to north of Santa Barbara. The LA metro area is around here. And this was selected as a plausible large event, not the worst case scenario, to try to study the impacts such an event would have. We've not had that in recorded times, and so the California was not well developed when the last event occurred in 1857 in that area. So we wanted to see what's going to be the impact. So I'm going to show you a video here that's accelerated in time. What you will see is the San Andreas Fault rupturing. This is the dashed line here from the south to the north. I want to highlight that the Los Angeles area here and some other areas, mostly where it looks flat, is where we have deep sedimentary basins and wave propagation changes there. So the higher values of ground motions are the white-ish. So you see the rupture starts near the Salton Sea there, propagates, and you see the wave front and the ground motions as they propagate. And then we have this bifurcation of the waves as the ground motions or the seismic waves start to enter the lower velocity structures of deep basins and so on. So simulations like this, even though this one is 10 years old, we run them all the time. We use a lot of supercomputer time for that, or high performance computing. The key thing here to see is that these waves here in these sedimentary basins tend to be trapped for a long time. And so that means that you have a lot of shaking over time. If we do similar simulation, but starting from the north, we don't see this combination of situation that creates those long period, long duration waves and so on, because it's a combination of directivity and basin response and so on. So this coupling is extremely important, and we've learned a lot from that, and that has helped a lot the modeling. So the shakeout scenario was once again selected as one possible big one, magnitude 7.8. The shaking lasted over 2 minutes based on the simulations in multiple areas. So large shaking, long duration, has an impact of lots of landslides, and that's where we get into this holistic. We heard about holistic approach here, about fire ignition. You saw recently how 2 small fire ignitions created a massive disaster, right? This relates to climate change and so on. We have a lot of issues with water as well. So all this is holistic. I'm focusing on earthquakes, but you can see that everything's tied together. The exercise led to these numbers, more than $200 billion in economic losses from 10 years ago and so on. So what was learned from that? Well, that was the largest emergency response exercise in US history. Involved all kinds of people, multiple researchers and groups. And it demonstrated that existing disaster plans were inadequate for an event of this scale, even in Los Angeles, who is probably one of the most prepared places. So it motivated a reformulation of the response and preparedness and so on. And it's a scientific basis of this report created by the Seismic Task Force, by the city of Los Angeles, Resilience by Design. So the report was released in 2014. And so again, 2008 to 2014. In 2015, the mayor of LA signed a historic mandatory building retrofit ordinance based on results from this shakeout scenario and the results. And just this year, also again acknowledging that resilience is a holistic problem or needs to be approached with holistic solutions, the mayor signed the Resilient LA Executive Directive that touches a lot of different resilience activities and so on. And the seismic strategies came from the Resilience by Design. So I'd call that a success story. So in addition, you may have heard of the Great Shakeout earthquake drills. That's where school organizations, families, individuals, all kinds of groups rehearse and prepare and test their emergency drills. In 2018, we had over 62 million people worldwide participating. You can learn more on shakeout.org. And one of the big tenets of this approach is that in most situations, you want to go and drop, cover, and hold on and really protect yourself, your head, and your neck, and so on. And the shakeout activities are coordinated by SCEC with multiple stakeholders, and there's now more than 25 different websites targeted to different languages and countries for that. So again, this is one place where preparedness and education is important. I want to talk briefly about Uniform California Earthquake Rupture Forecast. So we talked about earthquake rupture forecasts. That's a place, again, where using data from multiple sources, geodesy, geology, seismology, and whatnot, paleoseismology. And the group that worked on USURF 3 performed what we call a grand inversion to make sure that all the data could be assimilated to come up with new magnitude frequency distribution and slip rates and rates of earthquakes over time. USURF is the basis for the national seismic hazard maps that are used in building code applications, and it was done again large collaboration with a lot of people. So it's not a question of if, like most of the hazards and risk we're talking about, but a question of when. In California, it's pretty important. 2/3 of the long-term seismic risk comes from California. But hey, we're not safe here either. Just be aware. Earthquakes can happen anywhere. But so USERV-3, again, used for design, and the California Earthquake Authority, which is a nonprofit organization that sets earthquake insurance rates, saw that the advent of USERV-3 led to a reduction in insurance rates for homeowners, which is an impact as well. So I want to talk briefly about CyberShake. We talked about simulations a lot. We performed probabilistic seismic hazard analysis. CyberShake is a physics-based way of doing that. So again, we start with something like a USERV model with all the different ruptures where they can happen. We're going to now simulate upwards of 400,000 of them to represent a long time span. And we're going to model each of these faults with their rupture. We then have the 3D velocity structures of the region combined with seismic wave propagation codes. And then at a given site, we will obtain seismograms and intensity measures, ways to quantify the shaking. This gives us hazard curves. Most people are familiar with different hazards and basically representing that. We can disaggregate the hazard in terms of what magnitude, distance, contributions are important to our site. And from that, we can generate full 3D probabilistic seismic hazard maps that can help us in research. And the white dots you can see there represent different sites at which this is computed. So CyberShake is a very important tool, and it integrates a lot of things. So if we don't know anything about the Earth structure, we're going to model it as a cake, layered cake, just basically 1D layered structure. Even using CyberShake, which is a powerful tool, we will obtain a map that kind of looks like that. So we have a 1D velocity structure. If we integrate information from multiple sources to define our 3D velocity structure, the map looks like this. And it's really important because it gives us a better handle on where we can expect the largest hazard. So I don't have time to talk much about the CyberShake, project and its impact, but it's being validated and used in a lot of different ways so far. It's been used as the database for machine learning for the earthquake early warning system in California. So that's a really nice way to pretend you have earthquakes and how does the system function. It's a leading model in the USGS seismic hazard maps for localized areas. And it's a source of new design maps under consideration for building code applications, especially for tall buildings in the Southern California. So the important point here I wanted to make is that scientific research impacts risk and resilience. And to me, one of the biggest and most important component of having an impact is really to work in multidisciplinary teams. The collaborative nature of the work is critical, and involving stakeholders at multiple levels is how we go from science to engineering to policy and have an impact. So we've shown that practical risk reduction can impact the society by integration of science, and most of it is through uncertainty reduction, which I didn't have time much to address, but that's really a key point. And finally, critical resilience impacts can also be achieved by better education preparedness. And I want to thank you. So.
Okay. Okay, as we continue our speakers, as you can see, you have questions, you can email them to the addresses on the screen. The next speaker is Lisa Goddard. She's going to talk about climate and weather.
So thank you very much for the opportunity to talk to you today about building resilience to extreme weather and climate in developing countries. I'd like to motivate this discussion through the Sustainable Development Goals. So as many of you may be aware, there is one sustainable development goal that is really focused on climate action. But if you look across all of these SDGs, climate's a factor in almost all of them, some more directly than others. It's a stressor. It's a confounding factor to other stressors contributing to those goals. So climate information really should be part of the solution in all of the SDGs. Now, last year, Columbia University started a new initiative called Columbia World Projects. My institute is one of those leading one of the first of these large projects. And our project's called Act Today, which means adapting to, fill in the blank here, adapting food systems to climate today for tomorrow. And you can see that the goal that we've embraced in this project is effectively SDG 2 on zero hunger. Now, we at Columbia University and even our collaborators are not going to be able to achieve that goal ourselves, but we're working with countries and international organizations to help them achieve SDG 2. And we're doing that through building climate services that are coming through the lens of food and nutrition. Now, if you're going to do anything in the real world in climate, the first thing that you really need are good observations that have some ground truth to them. And that's really a problem in the developing world. As you can see in this map that's showing the density of rain gauge stations, the developing world is pretty sparse in those stations that are at least reporting to global data sets. That doesn't, and just to put this in context, the country of Germany is about 1% the land area size of the continent of Africa, but it has 40% more rain gauges reporting to these global data sets. The countries often have data, but it's not reporting out. They may not even be able to use it. Additionally, it's typically constrained to towns and roads. So one of the things that we're doing is to work with countries to help them clean their data, merge it with remote sensing products, bring in the technology, say online platforms that let them view, analyze, and disseminate that information to the people that they need to provide information to. And we also partner on trainings, both for the producers of climate information and the users of that information. But data is really critical, because if you can't understand the past and monitor the present, how are you going to provide good and relevant information about the future? Even so, there's many that have a very difficult time using climate information directly. So what I want to show you are two examples of the use of climate information to help facilitate preparedness and resilience. The first of these is forecast-based financing, and that's in the context of food security preparedness. This is work that's been done with the World Food Program. And the second example is climate-based index insurance. And here the context is building drought resilience for smallholder farmers. So starting with the forecast-based financing. This schematic here is, we're going to start, let's see if I can get my pointer. No, does the mouse not work here? No, the pointer won't show up. There we go. Okay. So the current business as usual plan for the humanitarian sector is to respond to a disaster once it occurs. So in this graph, as time is progressing from left to right, and the needs of those impacted communities is on the vertical axis, what you typically have is that once those needs start to increase, a crisis or a hazard has occurred, once the emergency is declared, then the humanitarian organizations can go out and ask for aid and come in and start supplying aid and address those vulnerable communities. After the event has subsided, maybe those communities are able to build back. Far too often, though, these vulnerable communities are hit very soon afterwards with yet another crisis. The idea of forecast-based financing is if you can anticipate this climate hazard, in this case, if you can anticipate that ahead of time, the crisis that would lead to a humanitarian crisis, with a pre-specified level of confidence, then that forecast can be the evidence to go out and appeal for aid so that those communities can prepare, and the humanitarian organizations can mobilize resources ahead of the disaster. And there's a building body of anecdotal evidence that's really showing that preparedness ahead of a disaster leads to faster response, less loss of lives, less displacement, and is also much cheaper. But the parameters of how this gets done really need to be worked out. So the way that we've prototyped it with the World Food Program is by focusing on forecasts for the hazards that impact food security. The first case we took on was for the Philippines, and what you're looking at is a drought forecast that's been cast and presented at the district level. So on the left, this map is showing the probability that the rainfall will not reach median. So this is a forecast for being drier than the, say, average conditions. This forecast was made in the fall of 2015, and as you know, this is a time when we had a very large El Nino event underway, and this is what we might expect for the Philippines, would be to be dry during an El Nino event. That not receiving average rainfall is extremely high probability for almost all the districts of the country. But maybe that's not a crisis level drought. On the right, you see a map of what if you're in the driest 10% of the historical record. So again, having that history, knowing what is the potential risk is an important element here. But so you can see that the forecast for that, again, probabilistically, still is very likely that in this upcoming growing season, the rainfall is going to be in the driest 10% of the years. So what are you going to do with that information? The idea is to take these probabilistic, in this case, drought forecasts, and turn that into a trigger for action. So the World Food Program is actively involved in this project to both identify what is, in this case, the drought risk that's the critical threshold, and how confident do you need to be in that forecast in order to motivate action. That then gets translated into a yes-no, which you see on the right, and then that's the indication for maybe local or country offices to mobilize resources. But that doesn't have to be just drought. For example, in the Philippines, even during this extreme drought that they actually did experience in 2015, 2016, there were a couple of tropical cyclones that came through. So you have also weather risks on top of climate risks, and those might actually be of opposite signals. And so it's possible to incorporate that as well. Here we have a potential trigger on tropical cyclones. You may have some districts where both of those things are at risk, and that can be identified as well. But these are happening at different time scales. They're coming from different forecast information. The determination of these thresholds and these triggers is a very deliberative process. And so we've built what we call a dashboard. It's all interactive that allows the technical parts of World Food Program to play with the information and think about where is there that trade-off between uncertainty and action. So this dashboard may have the actual forecast for an upcoming season. It may have, for a particular district in the country, the full distribution of the forecast may be compared to historical conditions. For that same district, we can look at the skill of predicting drought through the calendar year. Scrolling down, we might have, for a particular important season for the country, what's the skill over all of the districts. And very importantly, for defining how confident you need to be, is looking at the past performance of those forecasts. So how often have we indicated that action should be taken and that was warranted, that crisis actually occurred? How often did we not indicate that action should be taken, and that could be done confidently? There will be some times that action is taken in vain. This is probabilistic information, and that's this important balancing of what's the cost benefit to being wrong sometimes and still coming out ahead, particularly when it comes to human lives and livelihoods. The second example that I want to talk to you about is climate-based index insurance. Now, the context here is that in the developing world, about 80% of agriculture is still rain-fed. You may be in a situation, part of the world, where 1 in 5 years is a drought year. The farmers don't know which year that is. So farmers are very risk averse. They're going to plan as if every year is going to be a drought year. So they're very hesitant to take out loans for seeds or other inputs to their farms if there's a risk that they might not be able to pay them back. And that's where insurance comes in to potentially cover that risk. The difficulty for smallholder farmers, insurance has really been thought as almost an impossibility for smallholder farmers because you can't get an adjuster to go out there to all these little farms and actually assess losses. So enter climate index insurance. Climate hazards, weather hazards are of a larger geographic scale and they can be verified. The trick is to identify, again, what is that threshold in the weather or climate that would very likely lead to a loss of crops so that insurance can be paid out, and to actually monitor and validate that that has occurred so that the payouts can happen. So the idea is certainly to ensure those bad years, that the farmers can pay back their loans in those bad years, but also to open up the good years so that farmers can take the loans and actually come out ahead and move forward. So the participatory process in putting these contracts together is critically important. It involves meeting with the communities and with the farmers, identifying what were the bad years, and then looking into the climate record, what was going on in the climate system or the environment at large that were leading to those bad years, because this helps you identify what are the climate events and those thresholds that you're going to want to target the insurance towards. And then again, the validation, the assessment in real-time monitoring of what's been happening so that farmers that have been experiencing these climate hazards or weather hazards are able to have their payouts. And that's usually, the way that we've been doing it, a triangulation of different information. It can involve remote sensing of vegetation or precipitation. It may involve looking at soil moisture, local observations, even the farmers' observations as well, all come in. We're trying to triangulate because we know that these observations are not perfect, but if we get a number of them that are all pointing to the same level of potential loss for these farmers, we want them to be made whole. So these are two examples of how climate information can be used to help reduce risk and to build better preparedness. It's also uncertain information. I mean, that's something that we should keep. When we've heard throughout the presentations, this is not precise information. We have uncertainties, but that needs to be folded into the decision support system itself. And if it is, then uncertainty should not be an excuse for inaction. Because when it comes right down to it, there are no answers, there are only choices. And in the words of Dan Osgood, who's the head of IRI's financial instruments team, it's so easy to get it wrong, but it's really important to get it right if we're going to build resilience to extreme weather and climate. Thank you.
Okay, thank you, Lisa. The last presentation in this group of six is Daniel Swain, and just as a reminder, you can still, we have a few of your questions in. We'll have a panel after this where all six speakers will be asked questions and to respond to things, but let's hear what Daniel Swain has. Daniel.
I'm sorry.
It's your mouse.
Okay. Perfect. All right, well, thank you. And I just as yet another reminder, I'm sorry, I'm clicking the wrong thing there. Another reminder to send any questions to the email address on the screen for the panel to follow my talk right now. So today, what I would really like to talk about is something a little bit different than we often hear about when we talk about changes in precipitation in a warming world. And that's because I really want to talk about the changing character of precipitation in a warming world rather than changes in the overall amount of precipitation in a warming world, because I think this is a session on societal resilience, and I think it's the changes in the character of precipitation that are really going to drive a lot of the societal challenges that we face as a result of global warming related changes to the hydrological cycle. And we already know that global warming is probably going to increase global mean precipitation on the order of 1 to 3%, and that's because this is something that is essentially constrained by the energy balance of the Earth. This is something that is interesting, but in some ways a curiosity. 2 or 3% increase in global average precipitation maybe doesn't have a lot of practical implications. But on the other hand, at the same time that that's occurring, the amount of precipitation occurring in extreme events increases by a much larger number, on the order of 5 to 10% per degree Celsius of warming, so several times that of the global mean precipitation. And sort of referring back actually to one of the things we heard in the first talk today on sea level rise, the frequency of exceeding particularly high extreme precipitation thresholds increases at an even greater rate of much greater than 10% per degree Celsius of warming. So in a world we're headed for of at least several degrees of global mean warming, that's a very large relative increase in some places in the frequency of events that were either very rare historically or unprecedented. How can this possibly be the case? How can extreme precipitation be increasing much faster than the average precipitation, both in a global sense and in a local sense? Well, that is because essentially what we expect to see in the future is both wetting and drying at different times. And for the past decade, there has been a bit of a paradigm, sometimes called the rich get richer paradigm, or the wet get wetter, the dry get drier. That's actually been modified a bit in recent years. And the original paradigm essentially said that the wet places on Earth would become progressively wetter as the climate warmed, and the dry places that were already dry, drier still as the climate continued to warm. But it turns out that the modified version of this paradigm is really a similar argument, but in a temporal sense rather than a spatial sense. So rather than saying that the wet places get wetter and the dry places get drier, it's really that the dry times get drier and the wet times get wetter. And this is largely because we do know that there's going to be this large increase in the most extreme precipitation events pretty much everywhere, irrespective of whether a particular region becomes drier or wetter on average. And for that math to work out in the end, for there only to be a couple % per degree increase in the mean precipitation globally, there has to be a decrement occurring somewhere else. And essentially that's coming from an increased frequency of dry periods, both on daily scale in a lot of places where people live over the continents, and also on longer time scales in other parts of the globe, especially places that were already dry. Why is this happening? Well, the most straightforward answer is it's a fairly simple follow through of atmospheric thermodynamics. As temperatures increase, the saturation vapor pressure of water in the atmosphere increases exponentially, and so the ceiling, or the upper limit on extreme precipitation, increases very rapidly with rising temperatures. And the same thing happens with potential evaporation. So just the increase in temperature alone, just invoking some fairly straightforward thermodynamic arguments, you have an increase in hydroclimatic variability on both sides of the spectrum. And then you also have changes in atmospheric dynamics that are modulating this thermodynamic increase in extreme precipitation and in evaporation. And that has different effects in different regions during different seasons. But to a first order, this is really driven by one of the processes that we actually have greater confidence in from a climate modeling perspective, which is this thermodynamic contribution directly from the warming itself. Excuse me here, I seem to be losing my voice a little bit. So I just want to, I'm okay, thanks. I'll spare the plastic for now. So for a specific example here, I just want to point to some of the work that we did earlier this year in California, looking at increasing precipitation whiplash in the Pacific Southwest, which I think is a sort of a nice way of illustrating these ideas in a region where precipitation variability is already quite high, but is expected to increase pretty dramatically as the climate warms. And I think I can summarize the findings here in a pretty quick sentence, which is that we find a very large increase in the frequency of both wet extremes, so very wet years, and in very dry years at the same time when California's overall average precipitation, both in climate model simulations for the future and as we've observed historically, changes very little. So what's really happening is that these changes on opposing ends of the hydroclimatic spectrum are masking, are essentially the magnitude of the changes that are occurring. So the mean is not really being illustrative of the character of the precipitation we're expected to experience in the future. And just this figure up on the screen right now is essentially just pulling a data point out of those previous maps for a particular latitude, longitude in Southern California near Los Angeles, conveniently. And essentially you can see the purple curve is the average precipitation, the blue curve is the frequency increase in extreme precipitation, and the brown curve is the increase in extremely dry events. And what I think this shows fairly dramatically is that even in a place where the average precipitation changes by less than 20% in a dramatically warmer RCP 8.5 business as usual world, the frequency of extremes on both ends of the spectrum actually increases by 50 to 100% or more. So that's something you would miss if you only thought about the change in the average precipitation in a region like this. And this, I think, is true not just in California, but more broadly, where if we're only looking at the mean, we're not really going to find out much about the extremes, where the extremes are the things we're actually concerned about from the perspective of societal impacts. And I think this also suggests that more generally in climate science, it's really important that we think carefully about the metrics we use to describe both the present climate and future changes in climate, because if we're not using metrics capable of detecting these sorts of complex changes in the distribution of precipitation, then we aren't going to see them. We aren't going to find something that we aren't looking for. And just to illustrate why this is important, again using the example of California, I would remind anyone who doesn't remember or isn't familiar that California's previous largest wildfire on record occurred just last year in December, a time of year when the rainy season is typically in full swing. This year, or that year, it was considerably delayed. This fire has since been eclipsed by a new fire in the past 12 months, but that's another story. But just 1 month after this fire occurred in December, it was followed immediately by the sudden onset of heavy precipitation. So the fire season to rainy season transition in California last year took place over the course of about an hour rather than a full season. And this led to really devastating impacts. This was both a devastating wildfire for certain communities in Southern California, and the mud flows and debris flows that followed actually killed more people and damaged even more homes than the fires themselves in the first place. And yet, if you look only at the climatological average during that period, it was essentially a mostly sunny and breezy period with below average precipitation, which strikingly does not characterize the on-the-ground experience of anybody who actually lived through these disasters on the ground. So that's a specific example of how, if we only look at the average, we're really kind of going to miss the point. And this is especially true because from any societal impacts perspective, we almost exclusively care about far from mean state events. We're not that worried about times when conditions are slightly above or below average in some capacity. We care about times when conditions are much above or below average. And I think that brings me to my next point, which is that sometimes worst-case scenarios really do come to pass. And I think we've seen some examples of this in the United States in recent years, and I would really focus especially on Hurricane Harvey, which was essentially the precipitation associated with that event in Houston, Texas, just last year, was thought to be an essentially impossible event. Clearly, it was not. And I think there's been a lot of evidence in recent years, there's actually some peer-reviewed literature to back this up, that we systematically underestimate the likelihood of both extreme precipitation events in most regions and also in the subsequent inundations that follow. And this isn't even a statement about climate change. This is just a statement about the way we've been assessing the risk, the background risk of natural hazards, and that we've been systematically underestimating them in a flood context, in a hydrological context, for many years. And this really suggests that when we think about mega floods, these seemingly impossible events in the hydrological system, We know they're low probability events, but they're clearly also high consequence events, and that sort of begs the question of whether or not our hazard planning has lacked a certain degree of imagination. I think an example of this, again from California, is something that even people who live there, lifelong Californians, most of them have never heard of this event. The Great Flood of 1862, which the state of California now thinks is California's other big one. We heard about some of the original big ones, the big earthquakes either in the San Francisco Bay Area or in the Los Angeles region. But a repeat of the Great Flood of 1862 would be California's other big one. And the paleoclimate record suggests that great floods of this extreme magnitude occur every 200 years or so in the paleoclimate record. And that it's pretty clear that a modern day repeat would be disastrous for modern day California. The recent estimate is that a recurrence this century would cost something like $1 trillion, making it, as far as I know, one of the most expensive natural disasters ever to occur on Earth. What we found in our recent work, looking at climate model simulations for a business as usual future, is that there is a greater than 50% chance that an event like this occurs not by the end of the century, but just over the next 40 years. So this is something that really raised our eyebrows and sort of was a little bit alarming to us, because that's a pretty high risk of an event that would have quite catastrophic consequences over time horizons that we actually really do think about. The end of century still seems like it's a long time, but 40 years from now is really not all that long at all. And I think this presents a grand challenge to policymakers and decision makers and engineers, because really what it means is that a lot of our existing infrastructure is probably under-engineered for future climate. And in a very practical sense, what this means is that what we think is a fairly high level of flood protection, say 200-year flood protection, in the future and the not too distant future really may be more like 25 to 50-year flood protection, which has all sorts of insurance and natural hazard planning implications. And I think it also means, given that we see both not just an increase in flood, but also an increasing risk of drought simultaneously, is that the tension between these completing flood control and drought mitigation mandates in water-scarce regions like California are likely to be amplified. And I think that points to a broader point about facing reality, in the sense that climate mitigation ultimately reducing or bringing to zero net carbon emissions and stopping global warming so that the increase in extreme events tails off eventually is clearly a critical goal, but it isn't going to be enough, because there's a lot of momentum in the physical climate system and also in the social and political systems that are increasingly driving the climate system. So we're not going to be able to mitigate our way out of this. We're going to have to engage in real substantial adaptation moving forward. And I think a key point here in maintaining this resilience is that flexibility is going to be key. If we see increased whiplash in precipitation and in other climate variables, we're going to have to be able to respond and be nimble to changes of opposing character at different times. And so, given that that's the physical reality, it may actually be possible in some cases to harness one extreme to mitigate the risks of the other. And in a hydrological context, there are some specific examples of this already in California, where it may be possible to harness flood flows to mitigate drought risk by recharging groundwater and actually maintain environmental co-benefits at the same time. Flexible floodplain management and thinking more holistically about working with nature, and instead of trying to fight floods all the time, actually trying to embrace the fact that floods are going to happen, and how can we make them less destructive or even use them potentially in constructive ways. So just to close with a few closing thoughts here before we wrap up for the before we wrap up for the discussion. We're in the early stages of a new era of climate whiplash, and small mean trends in climate variables can mask much more consequential trends in the extremes. And climate science really needs to embrace this. We really need to be thinking about metrics and methods that are capable of capturing this sort of behavior, both in climate model simulations and in observations in the real world. We know enough about these risks to do something about it already. We don't have to wait, in some cases, for more information. We already know that the risks are increasing, so the question is, what are we going to do about it? And the answer is that we really need to engage in some forward-thinking adaptation, which is going to be challenging because it's going to require an unprecedented level of collaboration across institutions and across disciplines. And just a final note on that, to move a little bit in that direction, I just wanted to announce that that's what we're trying to do now at UCLA and NCAR and the Nature Conservancy, bringing forth a solutions-oriented approach to thinking about climate extremes in a warming world. Thank you.
Okay, so we'll have our discussion with the panel. Of course, it's a small place here for 6 people, but please come up, we'll find a way. It's a busy world as well, so. And Amir will take care of this.
All right, we just heard 6 fascinating talks from different fields, but all with common theme of societal resilience. So we received quite a few questions. Some of them were very specific about details of one particular talk, but we're gonna prioritize talks that are relevant to more than one speaker. And we hope that for each question, we get at least, or let's say 2 responses from different panel members so that we get different perspectives, but hopefully not from every single one so that we can move on to go through 3-4 questions. So the first question was motivated by Kava's point about measuring stress. The question for everyone is, how do we measure resilience, especially when we deal with a very complex system that has many different components? Where do we start? How do we start? Any thoughts and ideas? Go ahead.
I think, is it on? I think actually measurement is a wrong approach to these things, and that's a mistake we also made in case of sustainability with a lot of indicators we developed. Now the UN Environment System is also doing the same thing for SDGs, which is very problematic because the engineering approach to sustainability, resilience, and other things is to measure them. And the problem with doing this is that we normally focus on state monitoring rather than process monitoring. So there is a big literature on this that if you have a patient who comes to you're a doctor and the patient comes to you and you take the blood pressure and cholesterol and all these things and check and say everything is fine, come back in a year, and you forget to ask about his life habits. Has there has there been anything which has changed in his or her life? And you don't notice that he got divorced yesterday, started using alcohol, getting into drugs, and in a month might have a heart attack or something, then you miss the process. Unfortunately, we go by state indicators rather than process indicators.
Any other thought or idea from panel members? Please.
I'm hiding behind here. I'll just make a quick comment that a lot of times we measure things in terms of economic cost in dollars, because that speaks to a lot of people. But I think in the process of doing that, we ignore the very real cost of the currency of human lives, which gets masked when we focus too much on the economics of the situation.
Good point. So the next question was motivated by Lisa's presentation about forecast communication, but this is a question for everyone. What is the hardest part of communication? And when you communicate, let's say, forecast or other information, where do you start? Who do you talk to? And what's the challenge, basically, in the communication process? Lisa.
Since I'm motivated, I can start. So in the context of a climate, it's very important to start with forecasts that mean what they say. So we know that the climate is probabilistic. And so the predictions that we typically get directly out of models don't properly capture that. And there's a number of ways that people have been dealing with it. But if we have observations and we've run forecasts over past years, we can assess how well those forecasts work, both in their structure and their probabilistic uncertainty. So we want those forecasts to mean what they say. 70% risk, 70% of the time you say that hazard should occur. But that probabilistic information is sometimes a sticking point for people to use it because it seems very complicated. Even though we're using uncertain information all the time in our daily lives to make decisions, that seems very complicated. So I think an important element to making those forecasts more understandable by the people that we want to use them is to be able to translate what the climate risks are into what are the risks of the decision maker or the community that you're trying to inform. So that translation is a critical part, in my opinion, to the communication of that.
So a lot of work has been done around the world dealing with forecasts and probabilistic approaches, and there's two kind of school of thoughts that people don't understand probabilities, which is partly true, and that the New Zealand experience with earthquakes a few years ago showed that actually people started to really engage and understand probabilities. But I think using metrics that mean something to people and using the example of earthquake scenarios, some people criticize as, well, this is not what's going to happen. No, but this is kind of what could happen. It anchors things with numbers. You know, you will have that many fires. You will lose water service for so long. You will lose, access to roads and bridges. Makes it tangible to the public and people affected by them, and then they can feel more engaged in the process and what could happen. And even, again, for us, the earthquake drills are good for that because people realize, hold on a second, my kids are in school, my husband, or wife, or whatever, what relationship you're in, how do we communicate? Having a plan is, so these drills, I think, help make it more tangible. But I agree with, I think, at first, you talked about we're reactive and big catastrophic things are easier to react to. Earthquakes fall in this category. And even then, people forget, they don't prepare, and so on. So communicating risk and forecasts and all that, we need to tune different messages. And I think it's really important to have a strong group that helps make the message from the science point of view being understood by a larger community.
Just adding a thought from the air pollution world is that many times we're producing these forecasts and we're only considering a certain portion of the aspects that we're actually expecting to change because those are the ones that we can parameterize and quantify. So in the case of fine particulate matter, for example, and how climate change will influence air quality, some studies have limited their analysis to only how meteorological changes will affect air quality, not the emissions. And yet when you take a more complete picture and consider how the emissions will change as well, you get a very different result. So I think communicating not just what the outcome of your analysis is, but what was and was not included and how those excluded items can influence the result is important as well.
Great. By the way, I'm not reading the questions as they came. I'm trying to combine questions that were along the same line. All right, so we have a lot of experience with earthquake monitoring and developing design codes and so forth. We have around a century of experience. Is there any kind of information or approach that can be adopted for maybe sea level rise or addressing extreme precipitation or other types of events, maybe air quality or others? Any thoughts, any ideas based on what you heard from each other?
So I would actually say that the model that we have, again, from California in terms of how we deal with earthquakes is actually a good model for a lot of these sorts of extreme events in the climate system and the geophysical system, just because it offers a framework for thinking about these things before they happen, which we tend not to be very good at doing in a lot of different contexts. And that's actually part of the reason why we framed some of this analysis along the lines of, look, this big 1862 flood in California has already happened. There's a precedent for it. We kind of know. It's a sort of similar to the scenario-based approach. And I think that there are analogs for that in a lot of different sort of climate and extreme event contexts where, because it really is important to use metrics that are suited to the purpose and metrics that actually reach who you're trying to reach, this sort of approach of looking to history for analogs, essentially, and modeling scenarios on that basis, I think can definitely be a powerful tool. And I think, in that sense, a lot of the earthquake science has sort of led the charge.
Lisa.
So I think this is another place where climate prediction of the variability is an important part of the portfolio of information. So rather than just an assessment of how these risks may change in the future, whether it's extreme rainfall or these rapid, very large sea level events or wildfires, there are climate variability components to that. And we hear a lot of questions that are, what are going to be the impacts? How big are they going to be? When are they going to hit? And we can't necessarily answer that with specificity just from climate change projections. We might be able to understand how the risks change in the future, but not the actual event itself that we might be able to prepare for. And that's where weather forecasts, seasonal forecasts, and now this sort of growing area of subseasonal information, decadal forecasts, that whole spectrum of climate prediction that brings variability into the context of climate change, I think is really important for helping societies be better prepared to all of the risks that you heard about. Well, maybe not earthquakes so much, but maybe the potential impacts of climate following an earthquake disaster that would just compound those impacts even more.
All right. Any other thoughts? Shall we move on? Okay, so the other question is also related to communication and engagement with the public and policymakers. So in your opinion, as earth scientists, do we all need to be engaged? Do you think we all need to be engaged and talk to people, to the communities, to stakeholders, or is this something that should be left to climate communicators, let's say, people who have some expertise in communication and public engagement? Any thoughts and ideas?
I think it's everybody's responsibility, and we need to be better as scientists to help shepherd the message through, to really go from the science to the engineering or whatever application that can help solve the problems to policy. And that's where it's really difficult, and it helps. Not everybody has to do it, but key people in the community, in the science community who do the research, need to be involved in that, because in some ways it adds a level of credibility that is perceived from some people in the higher realm of politics. And we've seen a big success in, for example, an engineer in Oregon and Washington State who really made a big change by interfacing with politicians without becoming a politician, but leveraging our knowledge of engineering and so on to say, no, this is true, this is what's happening, these are the problems, and so on, and kind of helping with that. So I think it's everybody's responsibility, and we should not just expect, oh, policymakers will do that, or we'll have, lobbyists and so on. It needs to be really more holistic if we really want to have change.
So I think also that engagement happens on many levels. We all don't need to be out there giving public talks. We're not necessarily all suited for that or want to put ourselves out there, but one of the messages that I give to the public audiences I speak to is that the most important thing you can do when it comes to the issue of climate change is to talk to each other about it, because there's this silence that often wraps around the issue. People think it's too polarizing or contentious. They don't want to bring it up at a dinner party. And we can all do that. We can all talk to each other, because there's going to need to be a cultural shift for us to be able to deal with it. And if we can't talk about it, we won't be able to address it. So that's one level in which we all can participate. But I also think it's important to have both sides of scientists who may become more communication savvy, but also communicators who become more science savvy, right? And there's a role for both of those. And I do work more and more now with people whose expertise is in the communication side, and I have learned a lot from them that has helped me better to deliver that message. So I think it needs to come actually from both sides.
Yeah, I would just echo what Andrea was just saying about it needing to come from both sides, and the need to have communication savvy scientists be willing to engage on that level, and also to have the people who are experts in communication become really science savvy. And I think we're starting to see that. as a relatively young scientist, it almost seems like a bit of a generational shift in science, where there's a lot of motivation for doing that, I think, among the youngest couple of generations of scientists coming through the system now, which I think is good news.
I would just echo the sentiment that there's a number of different ways that scientists can engage with not just communicating to the public writ large, but getting engaged also in the public policy discussion. I think oftentimes our conversations about climate communication focuses mainly on communicating with the public, but I think there's this whole area of learning how to do science in a way that answers questions, provides data and metrics to decision makers, and using metrics and methods that can actually be immediately incorporated into what decision makers do. And so it's not just learning how to communicate to the public, but also learning what decision makers need. Maybe they do need valuation results, and so not just stopping at physical metrics or health metrics, but actually converting that to dollar values is something that is needed by the policymakers to inform their decision making. So it's not just necessarily public communication, but it's also learning the public policy process and engaging with that as well.
Lisa.
So I just want to add a slightly different direction, but related to the comments that have already been made. I think that scientists need to communicate more with each other. We're still incredibly siloed as disciplines, and the academic system doesn't help that. But we're starting to see, I think, steps in the right direction. My institute, the consortium that Daniel mentioned at the end, and I think that just the results that you were seeing across the talks really do indicate that there is activity going on in this cross-disciplinary way, but a lot more could happen, because we always think that all the complexity, all the uncertainty is in our own field, and we're just going to take the information, the tools from somebody else, and that's fine. But that's not always the case, and we don't know that unless we're working directly with those other communities.
Christine, you just mentioned a good example of a scientist getting involved in policy discussions and making a positive impact. Do you know of any negative impact potentially? It's scientists miscommunicating and causing more problems rather than.
So that's why we have a very strong group that's called CEO, Communication, Education, and Outreach, and I'm hoping to learn more and more from them. They're within SCEC. I think that, so we've had in the earthquake world issues like a scientist who goes on a press conference, oh, that was so exciting. Well, people died, Yeah. So things like that, being more mindful of how you communicate. We cannot say earthquakes are fun, even though it shakes, and I'm like, oh, it's a 6 at 100 kilometers, and we get excited because it's data, it's science. But that's one place where we can fail in communications and be aware of the impacts of what we communicate. And again, it's this whole multidisciplinary group. It's not just scientists, it's people who specialize in communication. And I think that's how we can have the most impact, working all together with engineers and eventually policymakers. Being too enthusiastic can be a problem, I think is the message.
Well, one more related thought to that is, aside from accidental miscommunication, there's also the purposeful twisting of words and taking them out of context, which happens a lot to scientists who speak about climate change. I know that every time I open my mouth in public, there's someone out there waiting to tweet out some words out of context and twist it around, right? So that's always going to happen, but I think there's a lot that we can do to defend that and to support each other in the messaging to overcome that.
I would just add to that, I think that the best way to fill the void where somebody might otherwise misquote willfully or otherwise science is to sort of publicize your own voice. I mean, make yourself known on your own terms and engage in that communication so that somebody else isn't speaking for you.
Mm-hmm. Sounds good. So maybe as our last question, so you come from different backgrounds, and you defined or talked about resiliency from different perspectives. Is there any synergy? Can you all work together? Or maybe as Lisa said, maybe working together, can you all sit down and write a proposal together on an idea related to this topic?
So I think that the idea is gaining traction, but the reality of academia and the funding streams it's really difficult to get these projects funded. So at SCEC, for example, we have to reach out to different programs to make sure that holistically we approach the earthquake system science problem. And we see a shift that NSF is coming up with those new convergent ideas and so on. But in reality, it's really hard to defend, and you have then multiple directorates who review the proposals and can make it hard to fund those. So I think there's a recognition, there's a need to work more together, but the reality is that, again, academia is still a lot siloed. I think in earthquake science and engineering, we've been more integrative and collaborative, and there's still a lot of work to be done, but there's a challenge there in getting the support and recognizing that sometimes you're going to solve a practical problem to try to understand what's going on, but certain entities will say, well, that's very interesting, but that's not necessarily fundamental science. And I disagree. Integration of multiple disciplines is really critical of us having an impact, both on the science front, because the issues of interfacing the uncertainties from one domain to the other are so critical. So I hope we're going to continue to have a change in that direction.
Yeah, I mean, go ahead.
No, please.
I would just say I guess these days I'm a bit of a poster child for the fact that there are some avenues, but it is still a challenge from a practical funding perspective. I mean, I currently work for UCLA, the Nature Conservancy, and the National Center for Atmospheric Research, because there is this joint interest in having these sorts of integrated conversations about the physical science and the environmental implications and the human implications. But you know, it's not easy, and there aren't really very many formal pathways. It's a cool collaboration, but it was definitely cobbled together from scratch. There really wasn't a pre-existing framework for it, and I think there is enough interest that people who are interested, I think, can start to approach it from that direction. But I think it is a challenge that there aren't more existing frameworks to have those sorts of conversations and to have that sort of engagement on the level that it really needs to be happening right now.
Just want to add one thing that I mean, people can work together, and a lot of times organic collaborations have been formed, and interdisciplinary, multidisciplinary, transdisciplinary approaches have been developed. But you know, these sorts of collaborations should be problem-driven, not fun-driven, and not like, you know, by the buzzwords driven. Unfortunately, that's the working model right now. We find a way. I mean, I'm sure now we sit down in 5 minutes, we can find climate change effects on this, and then resilient societies, and it would be a title and an abstract and then submit it. And we can publish papers together also. But the reality is that, I mean, the question to ask is, are we really solving a new problem? Was it necessary? I think we have this problem of bias towards our own you know, domains and also tools, and that's very scary. And yes, of course, the funding mechanisms that exist make us very reactive. And unfortunately, the funding agencies are normally behind, and there's a lag there. And by the time that they think a nexus of this and this and this is important, you know, scientists have already discovered that the nexus of so many other things are also important. But you have to limit your proposal to the nexus of this and this and this, and that's a problem. But I think those who really want to do it, they do it.
Thanks, everyone. It was a fascinating discussion. We are out of time. Let's thank our speakers one more time.